In this lecture, what we'll be doing is we'll be taking a look at reversible processes, and we will begin by giving a definition of what a reversible process is. That will be followed by a review of a reversible heat engine, and that is the Carnot cycle or the Carnot heat engine. And we'll conclude by taking a look at a Carnot refrigerator heat pump cycle. So let's begin by taking a look at reversible processes themselves. Now, in reality, no process is reversible. Every process that we'll be dealing with in the real world are irreversible. However, what we do in thermodynamics is we study reversible processes and we'll look at them as ideal cycles, because this would be the highest efficiency that we could achieve with any real world cycle, which we never will, because there are certain things in it that prevent us from having a reversible process. But to begin with, a reversible process, I'll give you a definition. So there's the definition of a reversible process. It says that it is a process that can be reversed without leaving any trace on the surroundings, so on the environment surrounding the system that we're looking at. And it also says that the net heat and net work exchange between the system and the surroundings is zero. So as I mentioned earlier, all real processes that exist are actually irreversible. And they're irreversible for a couple of reasons. So we're not able to actually achieve a reversible process. All processes are irreversible. Now, there are three main reasons why all real processes are irreversible. The first one is any system we develop is going to have some form of mechanical friction. So that could be friction from one surface rubbing against another. It could be pressure drop within the lines of our system with our working fluid. But we always have friction, and that represents taking energy and converting it into thermal energy, and once it becomes thermal energy, that is very difficult to recover, and it's an irreversibility. Another thing is non-quasi-equilibrium expansion and compression processes. We had talked about non-quasi-equilibrium earlier, but whenever we go through these processes, in order to have them in equilibrium, they have to go very, very slowly. And in reality, the processes that we study move quickly. And finally, in order to have reversible processes, heat transfer has to occur across an infinitesimal differential temperature, very, very small, which you never achieve in reality. And so as a result of that, all of the cycles that we look at, or all of the processes, are actually irreversible. And so just to summarize, though, we said friction was one of the things that leads to irreversibility. Another one is non-quasi-equilibrium expansion and compression. And finally, heat transfer across a finite temperature differential. Okay, so if that's the case, why should we even discuss reversible processes? Well, they represent idealizations, and they give us a good benchmark for how our real-world processes are compared, or how they're performing with respect to the reversible process, which would be the best that we could possibly do. So reversible processes So what we find is that reversible processes, what they will do, they deliver the greatest amount of work. So that would be in the case of an engine or a turbine. And also, if we're looking at devices that we're doing work on the fluid, they require the least amount of work. So the case of pumps or compressors. And consequently, they are good things for us to be able to study and look at them as being idealizations that we are trying to achieve, but in reality we cannot, because we always have irreversibilities in any system that we're examining.